Well, I appreciate everyone who's stopped in to hear about this. This is a project that I began working on about a year ago after I did a deep dive on multi-sig setups, both for myself and also to helping some others onboard into multi-sig. And anybody who's done multi-sig knows that there's a lot of friction involved, and I was really surprised at just how tedious and difficult it was. And so I guess I was inspired to think about how I could build a tool that would uh, take away some of that friction and some of the privacy concerns with that. So that's how it arose out of my mind. And then and there's not couldn't possibly have been a better um, foundation laid this week or this past week with everything going on with the coal card situation to just underscore how important multi-sig is. Um, I actually have a multi-sig setup that includes a coal card, and I was on vacation away from my coal card when all this news broke. And but I slept easily and slept well because my setup was in a multi-sig, so it wasn't dependent entirely on that one key. So multi-sig is really important, and particularly what this addresses is being able to set up a multi-sig uh, remotely without using tools that for communicating the information that might uh, reveal something that you don't want to reveal, in particular, most importantly, your descriptor. So that's kind of where I went with this, and also to be able to do this without getting people in the same room, particularly in a case where you have, say, political activists or something where it's risky to be in the same room or to be tracked to be in the same room or anything like that. It also creates a single point of failure. So to being able to set up a multi-sig with participants in remote distributed locations, I think is really important for this. So um, the coordination of the remote or the of the setup is the leaky step. So I'm just going to kind of go through the cryptographic reasoning here on how this thing works, um, and then I'll do a demo near the end of it. First of all, uh, in order to get the multisig set up, everyone has to share key material and put together a wallet descriptor. So you have to have communication among all the participants to do that. Again, you could put everybody in the same room, but that has its own risks. And so if you want to do it remotely, then that means there's a temptation to send that information over email or over a messaging app that you may or may not have uh, full control over the privacy of that. So, and then also once you get it set up, just to be able to spin from the multi-sig, especially if you've got remote participants, it's way better if you can do that over some kind of private channel. So the descriptor is particularly important because the descriptor itself, once you have that, you have a pretty significant privacy leak because you can then determine every address that will issue from that wallet and the balance of the wallet as long as you continue to use that setup. Also, you have metadata leaks that would reveal possibly you're coordinating with, when you're coordinating, and so forth. So, again, for activists and people like this is really important to be able to have a privacy solution for this. It also helps to take away some of the friction because, as we've seen, multi-sig is an important solution for lots of different risk factors in wallets. So I'm starting off with the threat model that the relay is the adversary. So we're assuming we cannot trust the relay, and that pretty much dictates how I set up everything. So We are going to assume that the relay could potentially record everything, try to read the contents, try to substitute handshake keys, possibly try a replay attack, and we need to be able to function even under those kinds of threats. So there are four guarantees in Keylay. First of all, the relay never learns plain text. All the cryptography happens in the browsers of the participants. There's no key substitution without already knowing the code. The code is the thing that sets up the initial channel and handshake. A code that's compromised later does not unlock past sessions. In other words, we have forward privacy. And then finally, private signing keys never enter Keylay at all. So Keylay is a coordination layer. It's not a wallet. So to begin with, we start with a session code, and a lot of this will become clear when I do a demo. But the session code is a minimum of 10 characters. It uses by default a pruned 31 character alphabet so that there's no confusion about things like 0 and O or pronunciations of certain letters. And this requirement produces a code of about 50 bits of entropy that would be shared out of band, either through a phone call, a piece of paper, signal, something like that. That will be shared among the participants. Right now, the way it works is it assumes just two participants at a time. My goal is to expand that out to be N participants, but for now it's just two. So that session code is used in two ways. First of all, it's used to derive a name for a WebSocket channel uh, through a hashing process. And then secondly, it's used to authenticate a handshake. So the session code derives an authenticates an HMAC key. So and uses expansion of the key. So you do 300,000 iterations in HMAC to make it difficult to do a brute force search attack. So then with that, we go to creating fresh keys. So both participants will create a public key and a private key, and then will authenticate their own public key because they have a shared code. And now both parties have the other one's public key and their own private key, and it's been authenticated through the code. So so there's no way that you can have a man in the middle attack with this particular approach, because that code at the beginning is the authentication layer that makes sure that no one else can just substitute a key into the process. So anyway, it's not a signature. It's basically an authentication. The authentication applies equally to both parties, so there's no distinction with the code among parties, so that you don't have an individual signature, but you do have authentication that everyone that is in the channel belongs there. So from there, we use an X25519 process. We multiply or combine your own private key with the other person's public key that they have shared with you and authenticated. And from there, you can derive a session key that is shared. Both parties know it. Both parties have this shared set of bits because they each have their own private key and the other one's public key. And by combining those properly, you derive the same shared bits. So from that, you can derive a session key that then can be used for encryption in both directions. So let's see. So this once you have that, then you basically just throw away the private key. That way, no one has ever shared a private key. That didn't have to cross the wire, and so it's going to be an ephemeral key, but that guarantees you forward secrecy. So that way, if let's say somebody wrote the code and the initial connecting code down on a piece of paper and shared it, and then somebody intercepted that code, they would not be able to go forward and reconstruct everything, this whole process going forward. Um, so let's see. All right. So basically, you can kind of see the process here. You start with the code. From there, you generate an HMAC key. That key authenticates the communication, specifically of the pub keys, public keys that are each that correspond to each participant's private key. Then with the other participant's public key, you multiply with the X25519 process, and then we sort those and create a hash-based derivation function, and then finally we land at the ability to do AES 256 GCM encryption, and we have a shared key for that process. The private keys that generated these public keys are nulled out so that there's no risk of those somehow being revealed at some point. So there are three possible attacks that could happen here, and this might be getting into the weeds a little more than we want to, but so we want to be able to send PSVTs, BSMS files, various blobs of data under AES 256 GCM encryption. So we want that to be able to detect if there's any kind of attack there. So a random 12-byte code is sent along with plain text, so that the an identical plain text does not give you the same ciphertext anymore. So we also add in a counter so that you can't do a replay attack. So both parties would expect the counter to have incremented each time. If the counter has not incremented, then that means that there's a potential replay attack underway. So with all these things together combined, then an attacker can't read the messages that are being passed because that's encrypted. They can't tamper with it because that's blocked by the GCM portion of the AES 256 algorithm here. And they can't replay because there's a counter in there that keeps it from being the same thing over and over. All right, so this kind of shows you the process from end to end. You have two participants, Alice and Bob, a relay in between. And so you share this session code out of band. Alice derives the channel name from the session code plus HMAC. Bob has the same code, so he does the same thing. And that way they can connect through a WebSocket connection. They derive the same channel name through that same process. Um, and so they're able to talk to each other over a WebSocket connection. I should mention at this point that my goal ultimately is to be able to do this over Nostr, so that you're not dependent on uh, a single point of failure with the WebSocket connection. But even now, anyone can run the WebSocket server. The code is there on GitHub, so anybody can download that and run that themselves. They don't have to trust my implementation of that relay. So from there, they generate these ephemeral key pairs, public and private. the Bob does the same thing. Then they swap the public keys with authentication through the code and make sure that they're actually talking to the person that has that code. Um, that guarantees forward secrecy. Um, once they've both done that, then the uh, they can verify that those are real. They use X25519 to generate the shared secret for AES. Um, and again, they can do that on both sides because both of them have that same information once they combine the public and private keys together. So now you have forward secrecy at this point. Now you can communicate in an encrypted fashion. Both parties have the key to do that. For as far as the relay is concerned, it's completely opaque, and the other party can decrypt. So counter in there, make sure that they check that, and so there's no replay attack there. So the relay itself, the only thing the relay knows is a channel hash, two pub keys, HMAC tags, and they know the size of the cipher text and the timing of the communication, and that's all. That's all they know. All right, so I think, yeah. So at this point, I want to try to do a little bit of a demo, and I discovered at the last moment when I was thinking of using my browser to scan a QR code that Zoom takes over my camera. And so I can't scan anything with my laptop, but I managed to scramble around and get another laptop going and my phone. So I'm going to do it that way. So first of all, let me change the share that I'm doing. If I can do that, I guess I have to. No, I think I can do it this way. Um, all right. So start with this. Okay, so if you go to keylay.org, that's just a website explaining all the details of how Keylay works. There's a button in the upper right corner that'll take you to the app. This is just running the same exact code that's on GitHub. And so this gives you an opportunity to start a session, and you can enter a code yourself here. You can make up a code if you want to, but it's preferable to just generate a random code because the algorithm is going to do a better job of getting higher entropy that way. So once you've created a random code in there, that becomes the code upon which the channel is built, and then you join session. Okay, so now it went through that whole process that we saw, but now it's waiting. Uh, let's see. It says waiting for peer handshake to complete. There's no one to talk to on the other end at this point. So if you're say wanted to send this through Signal or something, you can click copy there and copy it and paste it into a Signal app. What I'm going to do is I've got another laptop here that's off screen that I'm going to type in that same code. So let's say I get on the phone or type it into Signal, but suppose I just get on the phone with my partner and I say the channel code is W8EQFMUXJ5. So I just type that in to another Keylay session on another browser, and I click join session. Okay, so now it detected that another party has joined the session. Now we have two parties in the session. Currently, Keylay limits it to two parties, so no one else can join, and no one else can take over the channel either to prevent a DOS attack. So also, you'll notice that the sender, it says you are the sender there. the other side says you are a receiver, and I'll just show you what that looks like because you need to go both ways with it, but one at a time. So the receiver can claim the sender role, and when they claim the sender role, it automatically shifts the other party to the receiver role. So now you can see what it looks like when you're a receiver. And if you need to send something back the other way, you claim the sender role again. Okay, so I'm going to claim the sender role on the other laptop so that I can scan a code. And what I've done is I've just pulled up a Bitcoin receive address. And let me go back the other way so you can see what's going on. So on the other side, once in the sender role, I'm going to click Start Scan, and then I'll be able to scan a QR code. So I'm going to do that on the other side, and so basically instantly it picks up um, the QR code and sends it here. By the way, if anybody wants to do a screen grab and send me some Bitcoin, I'm happy for you to do that. But anyway, that's a received Bitcoin address. So that's just a single QR code, and that's a little easier. But also, if that's after you've set things up, you want to be able to coordinate spending. But also, we want to be able to set up um, the descriptor. So we need to be able to export a wallet setup, or even a preliminary setup from uh, from a wallet that we've started working on. I'm doing this from a Nunchuck wallet on my phone, and I'm going to export the wallet configuration uh, with a QR code option, and it uses BCUR2. And so this was a little bit more difficult because it will it's a video and it uses BCUR2, and sometimes it takes a minute for it to. So what I wish you could see, but I can't do it on the browser, is it shows you which frames have been read already, and which ones are remaining. So now it's done, and now it's created a BCUR2 on the other end. So on this end, now you're using this computer as a coordinator. You could use a hardware wallet to scan that QR code, um, and then without, violating the air gap, and you could use that process to uh, set up the multisig. So you can also download it, and depending on the type of QR code, you can download it. In this case, I haven't yet implemented decoding in the browser for the BCUR. So it assumes that the wallet that's reading this is going to read the raw BCUR, and then decode it in the wallet rather than in the browser. One of the next things I have to do is implement that in the browser. So at some point, I kept, with feature creep, I kept adding one more thing, and I finally was like, I need to draw a line just so I can get this thing out there at some point. So anyway, you can click download, and you can download something, but a it's not going to be the decoded version, so it won't be particularly useful unless you have a software decoder or something. So again, once you get all that assembled, if you want to go back the other direction and claim the sender role and then send it back, scan it and send it back to the other parties, you can do that. So that's basically what it does right now. Like I said, I want to be able to do multi-party uh, joins at the same time, and also to be able to do this where you don't have a WebSocket in relay in the middle, but it uses Noster in the middle. So one thing at a time, but that's where things are right now. All right. So
Okay. You have
couple of
more?
things.
Go.
Well, go ahead.
Oh, I was just, if you have a couple of more things, go ahead and share, and then we'll go to some Q&A, and
Okay.
then we'll.
Yeah, so just a couple of quick things. One of the things as I was going back through this, and this is one of about 12 projects I've been working on. So um, it's not like I'm working on this all the time. I had to kind of refresh my memory before I sat down to talk about it again. Is revisiting this, I realized I need to use the same code expansion process in the channel name as I do for the code itself for the authentication side of that. And currently it doesn't do that. So what that means is that the relay itself could, instead of taking 58 years to decode the underlying code, it might take GPU days to do that. If somebody was if a state level attacker was trying to do that, then they probably could. So I need to shore that up. That's one of the first fixes that I'm gonna do next. Um, and this one is kind of I'm not using a standard uh, Hake algorithm for the handshake where it'd be nice to do that, but what I've done, and I probably should have said it this at the beginning, but my design philosophy was only to use cryptographic primitives that are available in standard browser, already implemented in standard browsers in their libraries. So I didn't want to go to the step of either inlining code or writing my own cryptography code. I wanted stuff that was very well vetted and already being relied upon in browsers. So the problem is that this is not implemented in any browser that I know of, and from what I understand, that it's not even really seriously under discussion in the immediate future. So at this point, I'll just leave it as kind of a hand-rolled version, or not a hand-rolled version, but a kind of a makeshift alternative to that I've already implemented that uses the cryptographic primitives of the browser. Um, so another thing I'll have to go back and think a little bit more about is right now everyone ends up with the same authentication, so it doesn't distinguish one party from another because we're using a common code and the way it's being handled. Um, there's no distinction. So it's not like it's not a signature. It's just an authentication that you belong in the channel. So that's another thing I want to look at. Um, so just to mention here, these are kind of what I was saying here. As much as possible, I'm trying to use off-the-shelf um, functions that other people have developed and done the deep dive on that I have not. So I've tried to use standards and implementations that already exist out there. I should have mentioned that this handles BCUR as well as BBQR, um, and then uses standard PSBTs, BSMSs, and descriptors. Um, so yeah, these are just a few things to maybe talk about, but feel free to jump right
Thank
in
you.
now. That's at the end.
Anybody have any questions? Dan, Tagumi?